Now let us see another example. So let's compute the Laplace transform of t square exponential minus t. So we know that this is minus 1 to the power 2, the Laplace transform of exponential minus t s. So twice derivative. So d2 by ds2, and the Laplace transform of e to the power minus t is simply 1 over s plus 1. So we have to differentiate 1 over s plus 1 twice. So let's do that. Sorry, this is minus 1 square, so this goes away, it's just 1. And you have d over ds of minus 1 over s plus 1 whole squared. Once more we take the derivative, so we get minus 2 by s plus 1 whole cube. So you get in the end 2 over s plus 1 whole cube, and this is valid for s greater than 0, for example. So you can also have s greater than minus 1 here, but it is also valid for s greater than 0. Now for another example, let's look at the Laplace transform of t square cos of alpha t, where alpha is a constant, and we know that this is going to be minus 1 squared. The second derivative of the Laplace transform of cos alpha t, which is, as we know from our previous result, s over s square plus alpha squared. So first derivative of s over s square plus alpha square, let's compute that. This is nothing but s over 1 over s square plus alpha squared minus 2s squared over s square plus alpha squared whole squared, and this is equal to alpha square minus s squared by s square plus alpha square whole square. Now we have to differentiate it once more. So the derivative of alpha square minus s square by s square plus alpha square whole square, this is given by, so we can do it term by term. So the first is the derivative of 1 over s square plus alpha square whole square, and then the other term is the derivative of s square by s square plus alpha square whole square. So now let's differentiate this again term by term. So the first term we will get minus 2 times 2s over s square plus alpha square whole cube, and the second term we will get s squared. So let's first differentiate 2s by s square plus alpha square whole square minus s square 4s over s square plus alpha square whole cube. Now we can take s square plus alpha square whole cube in the denominator. So the first one we get minus 4 alpha square s, so this is from this part. Then you have 2s times s square plus alpha square, because there is a square here and there is a cube here, so we multiplied by s square plus s alpha square. And the third term is a plus 4s cube. Therefore in the end we get, so there is a cubic term with a 4 coefficient and a cubic term with a minus 2 coefficient, so we get 2s cube and minus 4 alpha square s and minus 2 alpha square s. From the second term we get minus 6 alpha square s over s square plus alpha square whole cube. This is the final answer, and this is valid for s greater than 0. So we have computed the Laplace transform of t square cos alpha t using this derivative rule. So one can do for higher powers as well, as long as one is willing to compute the derivative up to that order. Now let's come to the next property. This is division by t. So we would like to compute the Laplace transform of ft over t in terms of Laplace transform of ft. So the following theorem states that if limit t tends to 0 plus ft over t exists, then the Laplace transform of ft over t is equal to the integral from s to infinity f u du, where fu or fs is the Laplace transform of ft. So to prove this, first note that this condition for the limit makes it a piecewise continuous function, because as t tends to 0, if ft is if it is a continuous function, then there will be a vertical asymptote at t equal to 0. So we are excluding that kind of behavior, and we say that the limit t tends to 0 plus ft over t exists, so that it is a piecewise continuous on the whole interval 0 infinity with 0 included. So because we have also assumed that ft is of exponential order in this lecture, then this ft by t is piecewise continuous and also of exponential order, because since if t is greater than 1, then the modulus of ft by t is less than or equal to modulus of ft, because t is greater than or equal to 1, and this is by the exponential order property bounded above by m e to the power alpha t for some value of t naught. So we see that ft over t is also of exponential order. So ft over t is also of exponential order. So by our sufficient conditions for the existence of Laplace transform, we see that the Laplace transform of ft over t exists. Now the question is whether this formula is valid. So let us try to compute the Laplace transform of ft over t. This is by definition 0 to infinity ft over t exponential minus st dt. Now I am going to write 0 to infinity ft exponential minus st over t dt as another integral inside. So I am going to write integral. So first let me write ft and then integral s to infinity exponential minus ut du dt. Note that exponential s to infinity e to the minus ut du is nothing but exponential minus ut over t minus t s to infinity, but at infinity this is, so this is for u, at u equal to infinity this is 0, and at u equal to s this is minus exponential minus st over minus t, which is exponential minus st over t. So we have just taken this part and rewritten it as an integral. Now we assume that we can interchange the order of integration. So again there are sufficient conditions when you can do this, and there are cases where you cannot make an interchange for two repeated integrals. But again, since we have assumed that our ft is piecewise continuous and of exponential order, and that this limit t tends to 0 plus ft over t exists, then this will guarantee that this interchange of order of integration is allowed. So if this exists, then this is allowed. And so we can rewrite this as s to infinity, and then from 0 to infinity ft exponential minus ut dt du. So now note that this inner integral is simply the Laplace transform of small ft evaluated at the point u. So this is integral s to infinity fu du. So we get the required formula stated in the theorem. Now we have assumed this part. Again, we will see some sufficient conditions later on in the theory section, but for the moment we can assume that if you have a function of exponential order and this limit exists, then this interchange is allowed. Now let us see some examples which compute this integral, this Laplace transform. So let's compute the Laplace transform of sine t over t. So we know that this is, by the theorem above, integral s to infinity Laplace transform of sine t u du. Now the Laplace transform of sine t is simply 1 over u square plus 1. So this is in fact the integral du over u square plus 1, and this is a well known integral. The antiderivative is given by tan inverse u from s to infinity. So you get pi by 2 minus tan inverse of s, and for s positive this is valid, and in fact one can also write it as tan inverse of 1 over s. Using standard formulas for inverse trigonometric functions, we get tan inverse of 1 over s, and this is valid for s greater than 0. Let us look at another example. Note that we already know that the Laplace transform of t squared is given by 2 factorial by s cube, right? Now I will write this as t cube over t s, and check that you get the same formula 2 factorial over s cube using the integral formula that we just saw. So note that ft over t goes to 0 as t goes to 0. So here t cube over t goes to 0 plus is simply 0. So it exists, and therefore we can apply our theorem, and this is therefore nothing but the integral from s to infinity the Laplace transform of t cube at u du. This is nothing but the Laplace transform of t cube. We know that it is 3 factorial over u to the power 4 du. So we get 3 factorial outside, and then integral s to infinity du by u to the power 4. Now you can integrate it directly. You get u to the power minus 3 over minus 3 integrating from s to infinity. So you get minus 3 factorial over 3, and then at infinity you get a 0 term, and then at s you get s to the power minus 3, and so 1 3 cancels out, so you're left with 2 factorial here, so you will get 2 factorial over s cube, because this minus and this minus also cancels out. Therefore we see that we get the same formula using both by direct evaluation, which we did before, and also by this method of integration. So this is not really a new example, but it just illustrates that our formula works and gives us the same answer.